So another molecular scene problem, this time used to think about the extent of acid dissociation. So just as kind of an example, remember here when we have any weak acid, which we can kind of generically abbreviate HA, when we have that weak acid in water, that weak acid is going to dissociate partially. Some of these molecules will get to give up their protons to water, generating H3O plus and the conjugate base. So if we want to think about the extent of this, right, or the percent of this that dissociates, percent is always kind of part over whole. We can think about the concentration of HA that we have initially, and the part that gets to break up is the concentration of A minus that we're going to have afterwards. So A minus really represents the part that dissociated. And if we think about what we started with initially, this is really the whole that we have. So percent dissociation is going to be equal to the amount that's dissociated over the amount that we started with. And again, we're going to multiply this by 100 to give us a percent. So in this problem, it tells us that if we have a 0.15 molar solution of HA, it's going to be 33% dissociated. And so what we really need to do is we need to look at, how much acid did we start with, how much got to break apart, and then figure out which one is equal to 33%. So just as kind of a clarification for this problem, we can look in here and we can see all of these parts in solution. H3O plus are those guys. A minus are these guys. HA are these guys, right? But if we want to think about HA that we had initially, we really need to think about the HA concentration that we have at equilibrium plus the A minus at equilibrium. Because when we started this problem, we started with HA molecules that all looked like this. So to get the whole, we really need to add all of our green spheres. And hopefully that makes sense, because how much we started out with, okay, was all of it. We really need to think about HA initial as being both of these parts together, all slid over to the right as HA. Okay, so for all of these, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got 9. So the percent dissociation for all of these is going to have the HA initial as 9. And hopefully that makes sense. I don't know if I did a great job explaining it, but remember, we need to think about what the HA initial was. In order to get that, we need to consider the ones that got to lose their protons and the ones that still have their protons. Remember, these are equilibrium concentrations. To look at initial, we need to kind of back out and look backwards and say, well, both of these, combined together made our HA initial. And then again, to look for what's dissociated, okay, these are just only green spheres without the blue, right? Because that blue is that proton that's there. So we need to just count just the green spheres. So let's take each of our molecular scenes then and kind of do that, knowing that the denominator for each of these is going to be 9. And we need to find one that basically has a, if we want to look at a 33%, a 3 to 9. So let's look at molecular scene 1. Molecular scene 1, we can see 1, 2, 3, 4 of our dissociated species. So 4 over 9 is 44%. This is not the correct molecular scene. Our second one has 2 that are dissociated. This is 22%. Again, this is not the correct molecular scene. And we can already see for the third one, 3 over 9, that is equal to 33%. This is our correct molecular scene. So again, thinking about percent dissociation is the amount of acid that got to dissociate over what your initial concentration of your acid was, which at equilibrium is going to really represent both of these species.